Glass film heater. Electric film heater is used to heat up the window glass. Glass thickness is 8 mm and the film thickness is 0.01 mm. The power in the film can be regulated from 0 to 1000 watts per meter squared. Outside, the air temperature is minus 15 degrees Celsius. Inside, the air temperature is plus 20 degrees Celsius. Our task is to calculate the temperature of the glass. I'm going to use QuickField simulation software to conduct the virtual experiment. The model will be two-dimensional and the analysis type is steady-state heat transfer. Okay, let's start QuickField now. In QuickField, I create new problem. Glass. Next. Problem type is steady-state heat transfer. I am going to simulate only the cross-section of the glass, so the model class is plane parallel, two-dimensional. Length you need some millimeters. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You should draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. I'm going to draw it here from scratch. First, I'm going to insert a rectangle with the dimensions 1 by 8 millimeters, and the insert point will be here. Close, zoom to fit. This is the glass. The glass thickness is 8 millimeters. Now let's insert another rectangle on top of this one with the dimensions 1 by 0.01 millimeters. This would be the heating film, and the insert point is here. Close, again, let's zoom in. So this is the glass, this is the film. Let's assign labels. Through labels you can distinguish geometric objects one from another and explain their meaning. Switch to Select Objects mode, click the object to select, and type in the label name. Here this is glass and this is film. I'm going to calculate the temperature distribution, so I need to specify boundary conditions. This side is internal. Zoom to fit, and this side is external. Geometry model is ready. Now let's provide physical properties for these labels. Double click the label name in the tree. Glass thermal conductivity is 1. Film thermal conductivity is 4. Internal air temperature is 20 degrees. And there is some surface thermal resistance here. Here is the page from the ISO standard for the glasses. So at the internal surfaces, the surface resistance, thermal resistance, is 0.13. In QuickField, you should specify the reciprocal value, the convection coefficient. So here I type in 1 divided by 0.13. Okay, at the external side, again, I specify the convection boundary condition. The temperature is minus 15 degrees Celsius and the surface resistance is 0.04. So here I type in 1 divided by 0.04. Now everything is ready, and before I can run the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated, save all problem files and solve the problem. Let's take a look at the results. Here you can see the temperature distribution. The glass surface temperature at the outside is -7 and at the internal side is -5.5 degrees Celsius. You can adjust the field picture and switch on, for example, vectors of the heat flux. So the heat flux is directed from the warm side to the cold side, as it should be. You can use the contour tool, Select the external side and calculate the integral value of the heat flux. And the surface area is 1000 millimeters squared. So let's convert to watts per meter squared. This is 1000 times 10 to the power of minus 6 meters squared. I'm going to use the calculator. 200 watts per meter squared. These are the losses to the glass. Now I believe we would prefer to have the warm glass at the inside, so let's switch on the heater. Open the film block properties, and here I should specify the volume power of the heat source in watts per meter cubed. Let me explain what is it. If we have the surface area of 1 meter squared and the power of the heater is, for example, 500 watts. So we have the heating power of 500 watts per meter squared, but we need to convert to meter cubed. So we should divide this value by the thickness of the film, which is 0.01 millimeter. Okay, so for example, if we have the heater of 500 watts per meter squared, we should divide this by the film thickness, 0.01 millimeters. I should convert this to meters. And this will give us the volume power. Okay, let's copy this value, paste it here. I do not need here the dimensions. 500 watts per meter squared divided by the film thickness. Okay, let's solve the problem again. Now, at the external side, the temperature is +7, the glass surface temperature, and at the internal side, the glass surface temperature is +12 degrees Celsius. Let's calculate the heat flux. Again, I'm going to use the contour tool. Click to select this edge. The total flux at the external side is this value, watts per 1000 millimeters squared. Now let's zoom in. Contour, remove contour. .06 at the internal side per 1000 millimeters squared. And the difference between this value is caused by our heater. So this way you can conduct virtual experiments. You can change the power of the heater. You can simulate the glass behavior in different environmental conditions and get the temperature distribution. If you search for the glass film heater on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.